Hi, this is Professor Fernandez, and we're going to work on class note C in lesson 11. So the point of this example is to help you understand and work through this theorem up here. So let's talk about it. So this theorem says, let V be an n-dimensional vector space. So already there are two things I know about V. It is a vector space and it has dimension n. Then the following two things are true. If I find the same number of linearly independent vectors in V, as the dimension, right? Both of them are n. Then they also span V, and therefore they're a basis because they're Li and span. So in other words, if I know the dimension of the vector space and I find n linearly independent vectors, I do not have to also check that they span. That's what this first part of the theorem effectively helps us with. The second part is kind of the other half of that. If I know that those same n vectors span V, I don't have to check that they're linearly independent. Right? This second part of the theorem tells us that that follows. And again, therefore, they are a basis. So the real utility of this theorem is that it cuts down some of the work required to find a basis. Usually up to now, we have been showing that elements both are linearly independent and span before we can say they're a basis. In this theorem, if you know the dimension of the space and you find as many vectors, elements in the space that are either Li or span, then you know that they are a basis. So that's the real usefulness of this theorem. So let me illustrate it with this example down here. You might notice some things scratched out here. So I'm working off an older version of the notes, which had a different example. So this is the one that I'd like to do instead. So it says, we learned in the previous example that the dimension of R2 is 2. And in this theorem, we want to show that these vectors are another basis for R2. We actually did this using these exact two vectors in the previous example, but or I think in class notes A, but we did this check of these two vectors being a basis using the original definition of basis. So we checked that they were linearly independent and that they span. So this is going to be a little different in this example because I'm going to try to use this theorem. So you have two options that you can take with this example here. You can either show that the vectors x1 and x2 are linearly independent, or you can show that they span, right? And it's kind of up to you which one you do. I'm going to choose linearly independent because that's a little easier, although the span part is not that much more difficult for this example. So what am I going to show? So I want to show that if I take a linear combination of C1 and C2 and I set it equal to the zero vector in the space, does this imply that C1 equals C2 equals 0? Okay, so I'm going to set up this condition, C1, 1, 1 plus C2 minus 1, 1 equals 0, 0. And on the left-hand side, we've seen this before. This combines to the vector C1 minus, oops, I noticed that I put the minus in the wrong place. So the minus 1 should be down there. So this is C1 plus C2, and then C1 minus C2, and then equals 0, 0. Great, so this gives me the two equations, system of linear equations. C1 plus C2 equals 0, C1 minus C2 equals 0. If I add them, then I get 2C1 equals 0, so C1 equals 0, great. And then I can substitute that into any one of these two equations to give me C2 equals 0. Great. So indeed, if I go back up here, do I know this? Yes, I do, right? All the C's are 0. So we've shown, a little summary here, that x1 and x2 are two linearly independent vectors in the two-dimensional space R2. Great, so these numbers match up, right? We have found two linearly independent vectors in a two-dimensional space. So I'm going to scroll back up to the statement of the theorem, and that's exactly what I can use now for my to invoke the first part of the theorem, right? So it follows that they span. So it follows from the theorem 11.1.1, a lot of ones that they span R2. Okay, so that makes them a basis. Okay, so that's what we wanted to show. So these are another basis for R2. So again, this is a theorem that we will use a lot, and we will use this theorem because ooh, it doesn't even let me erase. That's interesting. We will use this theorem a lot going forward because it cuts down on the time to check that something is a basis, right? In many of the examples that we will do, we will know the dimension of the vector space. So I will often make use of exactly this red part that I highlighted by just checking that the elements that we're looking at are linearly independent, and then invoke this theorem and saying, hey, we know the dimension, we have the same number of linearly independent elements, so they automatically span their basis. Okay, so that's the end of this video.